Welcome to Iron Process, where some of the most advanced engineering processes on Earth come to life. Behind every structure is a highly complex sequence of operations that rarely meets the public eye, where massive equipment, cutting-edge technology, and skilled professionals operate in perfect synchronization. This is not only about how structures are built, but how they are engineered from the ground up with precision and long-term durability in mind. Let's get started. The tunneling operation using the TBM Karpatka on the S19 expressway in Poland represents a clear example of modern engineering capability and large-scale underground construction management. The process starts with logistics and transportation. TBM components are shipped by sea from Santander, Spain to Szczecin, Poland. From there, the equipment is transferred onto barges and moved along the Odra River to Opole. Oversized elements, particularly the cutter head and shield, are then transported to the Babika construction site using specialized multi-axle carriers. The total transported weight is approximately 5,000 tons, requiring precise coordination in both logistics and technical. Following mobilization, the project enters the assembly phase. At the southern launch shaft, the TBM is assembled into a full system, exceeding 100 meters in length, with a total weight between 4,000 and 5,000 tons, and a shield diameter greater than 15 meters. At the same time, an on-site facility for precast segment production is established to ensure a continuous supply of lining components. Once all preparations are complete, tunneling begins. The cutter head rotates to break and excavate the soil ahead, while excavated material is transported away through internal conveyor systems. At the same time, directly behind the cutter head, an erector installs precast concrete segments to form ring-shaped linings, creating the permanent tunnel structure. This excavation and lining cycle operates continuously, controlled by an integrated electro-hydraulic system and monitored around the clock from the control cabin. After more than 2.2 kilometers of excavation, the operation reaches the breakthrough stage. The cutter head penetrates the final geological layer at the receiving shaft, marking the completion of the first tunnel bore. The TBM is then dismantled, reassembled, and redeployed to construct the second tunnel. The Verdura 40 retaining wall system demonstrates a modern approach to earth retention, focusing on industrialization, construction efficiency, and long-term structural stability. The use of precast concrete blocks with a self-locking design reduces the need for mortar, speeds up installation, and ensures consistency across the structure. A clearly defined layer-by-layer construction sequence improves quality control at every stage. Additionally, the interaction between the wall and the backfill through controlled compaction, moisture regulation, and the use of geogrid reinforcement when required reflects the principles of a mechanically stabilized earth (MSE) system, enhancing load capacity and overall stability. The system also supports sustainability by enabling natural drainage and allowing vegetation to grow on the surface. Overall, this method is highly standardized, easy to apply, ensures consistent results, and adapts effectively to different site conditions. The system also supports sustainability by enabling natural drainage and allowing vegetation to grow on the surface. Overall, this method is highly standardized, easy to apply, ensures consistent results, and adapts effectively to different site conditions. The road rehabilitation process follows a carefully structured sequence of operations to ensure load capacity, durability, and long-term performance. It begins with milling the existing asphalt surface to remove damaged material and allow inspection of the underlying subgrade. The reclaimed material is then sorted, crushed, and reused as aggregate base, helping reduce both costs and environmental impact. Next, underground utilities are installed. Water supply and drainage systems are placed at precise elevations on a stabilized bedding layer, with elevation control achieved through laser-guided systems or precision leveling equipment. Backfilling is carried out in layers of approximately 50 to 60 centimeters, with proper compaction to prevent future settlement. After completing underground works, the subgrade is shaped to the final design level. In areas with weak soil, reinforcement materials such as geogrids or geotextiles are applied to improve load distribution. Base layers are then placed and compacted using rollers to achieve the required density. Curbs and drainage systems are constructed using slip-form paving, ensuring high accuracy. Finishing operations include joint treatment, surface finishing, and alignment verification. During asphalt paving, strict quality control is maintained. The surface is cleaned and coated with a tack layer to improve bonding. Hot mix asphalt is placed at the required thickness and compacted using controlled rolling patterns. Temperature control throughout this stage is essential for achieving optimal pavement quality. Finally, landscaping is completed by placing topsoil and planting grass to stabilize embankments and protect the roadway structure. The production process of spun concrete piles reflects a high degree of automation and strict quality management. Reinforcement steel is processed using automated systems for straightening, cutting, and forming end anchorages, ensuring geometric precision and reliable structural performance. During cage fabrication, automated welding produces consistent reinforcement cages with tightly controlled tolerances. Spiral reinforcement and spot welding enhance structural strength and stability. Concrete production uses high-strength mixes, typically ranging from C60 to C80, with electronic batching systems ensuring accurate proportioning. The reinforcement cage is placed into a steel mold together with end flanges. Once the required amount of concrete is introduced, the mold is sealed and secured using hydraulic systems. The critical stage is centrifugal spinning. The mold rotates at progressively higher speeds, distributing and compacting the concrete. Under centrifugal force, aggregates move outward while excess water and air move inward, increasing density and reducing porosity. A hollow core is formed along the pile axis. After spinning, the pile undergoes heat curing to accelerate strength development. Once sufficient strength is achieved, the mold is removed, and the pile continues curing to reach its full design strength. Finally, the finished piles are inspected, classified, and stored according to technical standards. One of the key methods is pure drive, a traditional impact driving technique using hydraulic hammers. The process begins with precise surveying and pile positioning. Spun pile segments are then lifted into place and driven into the ground using impact energy. Butt welding between pile segments is carried out in accordance with strict technical standards, ensuring structural continuity and uniform load transfer, allowing the piles to penetrate soil layers effectively. Particularly suitable for sites with favorable working conditions. In dense urban areas, the jack-and-pile method using static hydraulic pressing is applied to minimize vibration and noise. This system applies controlled compressive force to install piles gradually and accurately, with real-time monitoring of soil resistance. For more complex ground conditions, the full center auger method combined with toe grouting is used. An internal auger pre-drills the soil, and high-pressure grout is injected at the pile tip, strengthening the surrounding soil, increasing load-bearing capacity, and reducing settlement. The replacement of the Duffs and Marley bridges in New South Wales, Australia, represents a significant infrastructure upgrade. The original timber bridges, built in 1900 and 1926, had deteriorated over time under increasing traffic demands. Maintenance costs rose, and load limits were reduced, affecting transportation and the local economy. A full replacement project was initiated, but initial estimates reached $12 million, exceeding the available budget. Through optimized design and construction strategies, the total cost was reduced to $6.9 million, while maintaining a 2-year completion schedule. A notable highlight of the project was its adaptability and efficient design approach. Upon discovering indigenous artifacts at the planned Duffs Bridge site, the alignment was adjusted to follow the existing bridge footprint, preserving cultural heritage. At the same time, a standardized design approach was adopted for both bridges with nearly identical structural configurations. This allowed for component standardization, accelerated precast production, and reduced on-site construction time. The new bridges were designed as 3-span, 2-lane structures using modern pre-stressed concrete, capable of supporting loads up to 68 tons, meeting long-term heavy transport requirements. A notable highlight of the project was its adaptability and efficient design approach. Upon discovering indigenous artifacts at the planned Duff's Bridge site, the alignment was adjusted to follow the existing bridge footprint, preserving cultural heritage. At the same time, a standardized design approach was adopted for both bridges, with nearly identical structural configurations. This allowed for component standardization, accelerated precast production, and reduced on-site construction time. The new bridges were designed as 3-span, 2-lane structures, using modern pre-stressed concrete, capable of supporting loads up to 68 tons, meeting long-term heavy transport requirements. Heavy lifting equipment, including 500-ton cranes, was used to dismantle the existing structures and install new components efficiently. As a result, Duff's Bridge was completed and opened in November 2012, after only 7 days of road closure, 3 days ahead of schedule. Marley Bridge followed in April 2013. Despite challenges caused by 2 major flood events during construction, the project demonstrates strong technical execution and effective construction management. At the same time, it delivers clear community benefits by restoring full heavy vehicle access and supporting economic and tourism growth in the Greater Taree region. From historic timber bridges to modern pre-stressed concrete structures, the project represents more than a simple replacement. It reflects a transition towards safer, more durable, and more sustainable infrastructure systems. In the context of modern urban infrastructure development, the tram track rehabilitation and replacement project carried out by Eberhard stands out as a representative example, requiring precise technical control and strict scheduling. With construction taking place in confined urban spaces, the project not only improves transport performance, but also ensures operational safety and minimizes disruption to surrounding areas. The process is systematically organized, from the initial stage, including site surveying, traffic management, and the installation of lighting systems to support continuous operations. Demolition is executed in a controlled sequence, using rail plow attachments mounted on high-capacity excavators. This enables entire rail sections to be removed simultaneously rather than cut manually, significantly improving efficiency while maintaining consistency. At the same time, logistics operations are continuously maintained to manage large volumes of excavated material and ensure stable project progress. Following site clearance, the foundation is reconstructed using geotextiles and new gravel layers, combined with laser-controlled grading systems to achieve high-precision elevation control. In parallel, heavy equipment operations in confined areas are managed through modular disassembly and the use of heavy lift cranes, ensuring both safety and accuracy. In addition, vibration and noise control measures are implemented throughout the process to minimize environmental impact. Overall, the project demonstrates effective integration of modern technology, structured execution, and professional construction capability. Through this approach, Eberhard not only meets technical and scheduling requirements, but also reinforces its position in modern urban infrastructure construction. Zurich Airport is Switzerland's primary aviation hub, handling approximately 720 flights per day and serving around 25 million passengers annually. In this context, maintaining runway infrastructure quality is essential. In 2014, the rehabilitation of the central strip of runway 14/32, with a length of 3,300 meters and in operation since 1976, was carried out. This project represents a notable example of construction under simultaneous operation and upgrade conditions. Preparation began in 2009, with the main construction phase starting in 2012 and peak activity in 2014. The primary challenge was that all work had to be performed at night between 2200 and 600, requiring each operation to be completed within less than 8 hours before reopening the runway the following morning. The project was divided into 49 sections, each between 60 and 90 meters in length, executed in a repetitive sequence. Immediately after closure, more than 100 workers and 80 machines simultaneously removed a 30-centimeter thick concrete layer, totaling approximately 1,500 tons per night. This was followed by base treatment, installation of technical systems, and construction of new structural layers using GPS-controlled technology to ensure high precision. After completing intermediate layers, a 4-centimeter surface layer was placed simultaneously using multiple pavers operating in parallel, eliminating joints and optimizing surface smoothness. The subsequent grooving process plays a critical role in enhancing operational safety. project, commissioned by Flughafen Zurich AG, required a total investment of approximately 70 million Swiss francs. Replacing 36,000 cubic meters of old concrete with 38,000 cubic meters of new asphalt extended the runway's service life by at least 30 years, establishing a benchmark for rehabilitation under continuous operation conditions. The pressure pipeline rehabilitation project at the Gladalp hydropower plant, executed from the Sali station in a rugged alpine environment, represents a high level of technical expertise and construction management in energy infrastructure. Under conditions of steep terrain, confined space, and a strict one-year schedule, the project was executed with high precision from the preparation phase. The tunnel alignment was scanned and modeled in detailed 3D prior to construction, minimizing deviation. The existing pipeline was dismantled in a coordinated and systematic manner, stabilizing the workflow after initial challenges. Demolition of the old concrete foundation was then carried out using rail-mounted systems equipped with high-capacity hydraulic breakers in confined conditions. At the same time, meltwater from alpine snow continuously entered the tunnel, requiring constant pumping to maintain dry working conditions. The installation phase was critical, involving more than 1.3 kilometers of pipeline and 148 high-precision welds executed on slopes of up to 45 degrees. Logistics were tightly coordinated, combining cranes, specialized transport systems, and cable-assisted movement to transport multi-ton pipe sections into the mountain. Each section was precisely aligned and secured with support structures. Welding operations required both high technical expertise and physical endurance, as work was carried out under low-light conditions, dust exposure, and steep gradients. This resulted in a physically demanding process, requiring continuous movement along 45-degree slopes. Under these conditions, safety depended heavily on coordination, teamwork, and operational discipline. Upon completion, all welds were inspected using ultrasonic and X-ray testing. followed by protective coating and final connection to the turbine through high-pressure expansion joints. Completing over 1.3 kilometers of pipeline with nearly 150 welds under extreme alpine conditions represents a significant engineering achievement. The drain-based system by Eco Products provides a foundational solution for artificial turf applications, designed to ensure rapid drainage and structural stability. Installation begins with sub-base preparation, creating a level and well-compacted surface with appropriate drainage slope. Drain-based panels with a honeycomb structure are then installed and connected to form a continuous layer that provides load support and efficient water flow. Edges are trimmed and anchor points are installed to secure the turf system. The artificial turf is then laid, aligned, and fixed using screws at designated anchor points, ensuring stability without affecting drainage performance. The surface is brushed to achieve uniformity and a clean finish. The open cell structure enables rapid water drainage, maintaining a dry surface and long-term durability. The silo wrap strengthening method represents a modern approach to structural rehabilitation, where reinforcement is applied directly to the existing structure instead of demolition. Performance depends on the combination of advanced composite materials and precise application techniques, particularly in surface preparation and bonding quality. The use of continuous circumferential wrapping enables effective stress redistribution and long-term crack control. Overall, this method is efficient, streamlined, and highly practical, reflecting professional expertise in modern structural strengthening solutions. What defines these processes is not any individual technology, but how the entire system operates as a unified structure. From preparation to execution and quality control, each stage is interconnected and aligned with its technical objective. Modern construction depends on the ability to manage and control the entire workflow, rather than relying on isolated experience. When each stage performs correctly and in coordination, quality becomes an inevitable result of a well-structured process from the very beginning. Thank you for watching. If you enjoy content like this, don't forget to like, share, and subscribe. This is Iron Process. See you in the next video.